Today I'm going to talk about ViBand, a technique that enables high-fidelity bioacoustic sensing. This work was done with my brilliant collaborator, Robert Xiao, and my advisor, Chris Harrison. Today, smartwatches are mostly being used as an extension of people's smartphones. So sending notifications, discreetly and quickly looking up information, etc. But if you think about it, a smartwatch is a computer on your wrist, and it has a lot of potential to do so much more. Because unlike most computing devices, watches are unique in that they reside on the body. And the hand serves as a direct gateway to glean upon rich contextual information across a wide range of tasks, immediate activities, modes of engagement, and physical contexts. So a wearable device like a smartwatch is really a tool that allows us to explore our vision of transforming the user's arms and hands into an expressive sensing and input platform. It turns out that the watch's position on the wrist makes it ideal for capturing micro vibrations such as bioacoustics propagating through the user's hands. And in this talk, I'm going to explain how this is done. And more importantly, we'll explore a range of applications that is made possible with this technique. But before we dive into the details, let's go quickly through related work. First, there's a trajectory of research on worn bioacoustics dating back more than a decade, specifically Amento's The Sound of One Hand, Hambone, Skinput, and Mujibiya's The Sound of Touch. And then there's wearable form factors that rely on accelerometer-based sensing and event detection. However, majority of these approaches rely on custom hardware or cumbersome instrumentation, which limits the potential for eventual adoption. Although all modern smartwatches contain accelerometers, their APIs generally limit the sampling rate to around 100 Hz, as you see here. But this is sufficient for its main purpose, detecting the orientation of the device. For example, whether the arm is resting or whether it's raised, like this. But it turns out that existing accelerometers can operate at a rarely used high-speed mode. By modifying the smartwatch kernel and writing our own custom driver, we enable accelerometer operation at 4,000 times per second. And this incredibly high speeds, the watch can detect micro vibrations propagating through the user's arm. So let me show you a live demo. I'm going to open this view right here. You guys can see that. So at the top is 100 Hz accelerometer data. The middle is 4,000 Hz accelerometer data. And the bottom is microphone. So you can see the microphone is very noisy. I'm talking right now, and then it's generating all these different signals. So that's not good if you're just using the microphone because it's coupled through air. There's a lot of noise in there. But if you look at the 100 Hz accelerometer, it's only sampling at very long intervals, but then the 4,000 Hz accelerometer is very fine-tuned. So if I do all these fine motions, you can see that it's being captured by the 4,000 Hz accelerometer, but not on the 100 Hz accelerometer. This event is more apparent if I use something like a motor that has a very specific oscillation frequency. So here, my hand is away from the toothbrush, but then when I start touching it, you see all those sinusoids, really tiny sinusoid under the 4,000 Hz signal. You can see them in the 4,000 Hz accelerometer, but you can't barely see them in the 100 Hz. It's just not possible to see that. So here, you're enabling a range of applications already just by increasing the sampling rate from 100 Hz to 4,000 Hz. Okay, so let's go through a different view here. You have the instantaneous signal over there. Let's do a spectrogram of the actual signal. So let's plot the frequency over time. Just going to drag this real quickly. So here the data is loading. What I'm about to show you is the actual spectrogram. Right here. So you see the data is moving from left to right. So when I do these different motions, that's the 4,000 sampling accelerometer live. So when I perform all these different gestures, when I clap my hand or whether I scratch my hand over here or whether I rub, you could see all those different signals are very, very distinct. For example, if I also use an object like this, you could see the frequency, like it's just basically like a line oscillating very, very closely. When I get a power drill right here, you can see that the sinusoids are exactly different, right? very, very distinct. And if I use my iPhone over here, you can see the pulses right there. I mean, you can't capture this from a 100 hertz accelerometer, but at this sampling rate, you basically see the data as bioacoustics. And the cool thing is that everything is coupled to your body, not over air. So this only happens when you touch something. So that enables a whole suite of different possibilities. And so what I'm going to do next is actually, this data was trained with data from like a week ago, trained on one user. So it allowed it to detect different gestures such as, pinch or flick gestures. Okay, flick's not working, but pinch is working. So once you have that, you can actually use this and feed it into certain applications. So for example, I'm going to use this to advance my slides. So that's slide 1, slide 2, slide 4. Okay, so I'm just going to try and keep this going until the end of my talk. We'll see if it works. Okay, so what you just saw was high-speed accelerometer data live and in real time. So how did we do that? Let's go through the implementation. It turns out that existing accelerometers already have this capability. This is a teardown of the exact watch that you just saw in the demo. This is an LGG watch. It has an InvenSense MPU 6515. Okay. Go back. Too fast. It has an InvenSense MPU 6515 inertial measurement unit. This IMU series is actually widely used and can also be found in the Moto 360 smartwatch, the Samsung Gear 2, the Galaxy Urbane, and many other smartwatches. And indeed, most modern accelerometers support high-speed modes. To access this high-speed mode, we wrote a custom kernel driver. More specifically, the driver communicates to the accelerometer over I2C, requesting data in high-speed mode. So actually, this entire pipeline is software only, which can be enabled entirely in software, and no hardware modifications are needed. This means that this capability can be pushed to existing devices through as simple as a software update. So next, let me talk about the signal processing pipeline. First, high-speed accelerometer data comes from 3 sources. You got the X, Y, and Z. Well, you don't need all 3. What you really want is a combination of all 3, which gives you orientation independence. So if you rotate your hand differently, you're not dependent on either X, Y, or Z axis. So we fuse those 3 signals by taking the max across all 3 at any point in time. Next, we compute the FFT of that time domain signal, giving us the frequency information. We then use a small window to smooth the signal. And then finally, we compute the features across the windowed signal. So these features include power information, statistical features, mean, standard deviation. And we also take the first derivative and the spectral band ratios, which offers a more robust characterization of the actual signal. So the features are then fed to a machine learning engine, in our case an SVM. And in addition to machine learning, these features can also be used directly to power bioacoustic applications. Okay. So our technique enables novel interactions in 3 distinct application domains. So first, our technique can be used to classify hand gestures, such as flicks, claps, scratches, and taps. Here you can see a user tapping on the skin, which creates distinctive micro vibrations that propagate through the arm. And here I'm like swinging my arm, trying to show you that it's robust to unintended oscillations. Here we can classify one-handed gestures. Two-handed gestures are also possible. And it turns out that if you combine these actions with motion tracking, we can enable a variety of input modalities, such as buttons, sliders, radial knobs. You could also do counters. You could do hierarchical navigation and positional tracking. Yeah, let's move to the next slide. In addition to these gestures, our sensing approach can also be used to identify grasp objects. So when a user operates a mechanical or motor-powered device, those vibrations transfer to the operator. Here's an example of different devices. Did you guys hear that? Okay. So here's an acoustic guitar, you get a toy car, different types of power equipment, even like passive objects like a hacksaw and a panel saw. You can have like shop vac, a nail gun, all these different assortments of mechanical power devices. In our previous project, M-Sense, some of these objects we can't detect because there's not enough electromagnetic emissions, but this approach can complement that technique. Here we're just basically using the mechanical vibrations of these objects. Okay, so the first thing that you saw was, the first two were passive. Next we're going to do, it turns out you could do structured vibrations. So what we mean by structured vibrations is kind of like you're controlling the actuation. You can think about it as like structured light. So in order for you to do this, you'll need a transducer. So we took off an off-the-shelf transducer, and a unique capability of this is that events are only triggered upon touch. And then we used the transducer to emit structured vibration patterns for our data. We used 4 classical transmission schemes, which I'll go through very quickly. So ASK, which varies the amplitude of the carrier signal. You have FSK, which varies the frequency of the signal. You've got PSK, which varies the phase shift of the signal with respect to a fixed reference. And finally, QAM, quadrature amplitude modulation, which is a combination of phase and amplitude. So here's an example of a 8 QAM constellation diagram. This is grabbed from Wikipedia. The x-axis is the amplitude information, and the y-axis is the phase. So each dot actually represents a symbol. So for example, if you see a phase modulation in the upper quadrant, shown in red here, it encodes a binary sequence, like 1-1. So this particular example is called 8 QAM, but we can also use 16 QAM, so you use 16 symbols. And as another reference, your LTE on your smartphone actually uses 64 QAM. So at that point, we use error correction in all of these schemes to make the transmission more robust. So really quickly, we add an 8-bit CRC to the encoded signal plus a Reed-Solomon error correction code. So in total, we have the message plus the CRC plus the ECC code as the final data packet. So here's an example of FSK transmission, which we vary the frequency. So when you touch, you get all the frequency information by varying that part. And when you're not touching it, you don't see any data. And here's a quick demo of full packet transmission. It's a little too hard to see the text on the watch, but you can see the full HD video on my website. Okay. So what I've shown you so far are 3 application domains utilizing high-fidelity bioacoustic sensing: gestures, objects, and structured vibrations. So how good is our technique? We conducted several user studies to address critical questions on feasibility and accuracy across different application contexts. So we recruited 17 users. They all happen to be right-handed, but our technique is agnostic to handedness. And since bioacoustic signals can be affected by different anatomical configurations of the user, we also recorded the body mass index. So in study 1, we tested several facets of gesture recognition. We used a per-user gesture training and trained across different models and different gesture sets. And then we trained 15 instances per gesture and tested everything live. So in wearables, repeatability is important. So we included that in our study design. We tested once, removed the watch, and then tested it again, which allowed us to compare the performance drop-off. So here's a diagram of all the different gesture sets: 2-handed gestures, 1-handed gestures, and on-body input. And here are the results. Across 17 users, 17 gestures, the average combined accuracy is 94%. Jumping to my previous notion about bioacoustic being sensitive, for pre versus post-watch removal, we saw a mean accuracy drop-off of about 5%, which isn't terrible, but it's also not a slam dunk. So next, for study number 2, we evaluated object detection. We obtained 27 objects dispersed across 6 locations. We built a machine learning model trained on a single person, and 4 weeks later, this model was tested on 17 users. And we also wanted to figure out whether there is a difference across different watches, or identical watches, actually. So we trained our model on watch A, and then tested it on watch A or B. And finally, we also tested repeatability, just like the previous study. So we test once, remove the watch, test it again. So users visited all 6 locations, and object order was randomized per location. And here's the set of objects that we tested spanning 6 locations. A key feature of this diagram is that on the left side, there's a little line there. That is actually 100 hertz accelerometer data. If you're only looking at 100 hertz, that's what you're getting. So you're really looking at something really tiny if you just limit it to 100 hertz. So we saw no accuracy differences between watch A or B, and saw no differences between pre- and post-watch removal. So we combined the accuracy results for all conditions. Here are the results across 27 objects, 17 users, with a machine learning model tested on 1 user and trained 4 weeks prior. Our technique achieved an average accuracy of 94%. So another key thing I want to insert here is that while doing object detection, we also performed a false positive robustness study, where we ask participants to perform rigorous activities. We train our model with a large set of negative examples in this case. And these events were performed during transition periods across different locations. So users were walking for 2 minutes, jogging in place, washing their hands, etc. The other thing while we're talking about this part, I want to show you that even if I shake my hand and slap my face here or do these different things, it's not triggering the clicks. But then when I do the pinching gesture, it triggers to the next slide. So it's really robust to some of these unintended oscillations that you're trying to do. Okay, so let's go through the false positive result robustness study. Across 17 users, 77 minutes, a total of 6 false positive triggers were seen in that event. So 12 of the 17 participants triggered no false positives. I'm just going to quickly run through all the other slides. There's still a lot to pack in. So finally, we tested transmission accuracies of structured vibrations. We selected the 5 transmission modes listed here, 4 FSK, 4 PSK, 8 PSK, 8 QAM, and 16 QAM. And we selected transmission over finger, and transmission over palm, with 4 rounds of data collected. So here are the results. So 4 PSK achieved the best performance with a bit error rate of 1%. 1% at 200 bits per second. To put this result in context, prior work on bone conduction data transmission operated at about 5 bits per second. More details on these results can be found in the paper. So finally, here's a constellation diagram. The left one is what you saw in the Wikipedia example, and the right one is the 8 QAM constellation diagram we captured from all of our users. You can see that the distinct patterns are very clear and obvious. And then here's the constellation diagrams for 4 PSK, 8 PSK, and 16 QAM. So like all approaches, our technique has pros and cons. Let me go through them really quickly. So many competing oscillations experienced by the arm. So a good recognition system needs to filter out the true signal from unintended noise. Also, physical coupling can affect how micro vibrations propagate through the arm. But because we're using frequency information, we are less susceptible to variances in amplitude. We're looking at only frequency, so that's a little bit more robust. And lastly, our current implementation will have a toll on battery life, because we're merely hacking to get around a default setting. But it's always possible to implement ViBand as a system on chip, like the same ones that you use for OK Google and Hey Siri. I don't think I have enough time to go through each example applications, but you can look at the video in our website, and you'll get a sense of all the different applications you could do when you have the ability to sense bioacoustic through a smartwatch. The video online should give you a full view of what these applications are. And that is my talk. So we believe our approach unlocks a wide range of user interface techniques that previously relied on cumbersome hardware. In addition, as you've seen in this talk, this capability can be deployed to existing smartwatches through a simple software update. That's the end of my talk. Thank you for your attention, and I open the floor for questions.
Okay, so I'm going to ask the next presenter to set up. If we have any questions, we have time for 1 or 2 over there. Can you please introduce yourself?
Manohar from Microsoft Research, Bangalore. the object recognition case, I did not understand the significance of the 3-week delay. It's about machine learning and not about individual users. So why is the 3-week delay significant?
So the question was, why was there a three-week delay?
Why is it important? Because it is about the machine learning.
Oh, I see. Okay. So the importance about the 3-week delay is that we wanted to make sure that the object vibration signatures are consistent over time. That's one way we wanted to test, because objects might change their configuration or whatever. So it was important to have a really long time lag, because that's how things are going to be operated in the real world. And it turns out 4 weeks prior, our machine learning signals are still pretty good.
Okay, we'll take it there then. Thank you very much.
Thank you.
Okay, so next up we have a paper